Okay, so that's entropy. Entropy tells us how pure or impure one subset is. Now what we need to do is we need to aggregate the information from several different subsets. Because remember, we're splitting on the weather, and it has 3 different subsets, and each one of them will have a different purity value. So how do you put them together? Well, basically you just average them, but you don't just do a simple average, right? So I guess to see why you don't do a simple average, so suppose I have some attribute, right, and I had 10 examples, and I have 2 subsets, and this is pure, and this is totally impure. So the entropy here is, let's say, 1. But maybe this guy had 8 examples, and this guy had 2 examples. Right? Or I could have another split which splits the same 10 items on attribute B, and now I have 6 and 4. Right? And this is maybe totally pure. Or no, actually, let's do it the other way around. Right? So this is 1, and this is 9, and this is totally pure. And this is, well, it can't be 1, but it's sort of approximately 1, almost. Okay. So if I have an example like that, right, 2 different attributes, 2 different splits, in both cases you have a pure set with a 0 entropy, and you have an impure set with an entropy of almost 1. Right? But which one is better? Which one do you like better? The right one. Why? Yeah, so basically think about, so the answer was it's going to be harder to split the other one. Think about how much splitting you have left to do. Here, you're going to be splitting this set, and this set only has 2 items. Right? So odds are it's probably going to be very easy to find a split, because there's only 2 of them. Here, you're going to be splitting 9 items. So both of them achieved a pure split and an impure split, but one of them, the pure split, covered lots of examples. So we classified lots of our examples well and misclassified a few of them, or still need to classify a few of them. Right? In the other cases, yeah, we classified one example correctly, yeah. So we're still left with n minus 1. It's not very good. So the way this is taken into account is when you are adding up the entropy values, you put a weight on each entropy. You put a weight on each subset. And the weight is the size of that subset divided by the overall number of examples that we have at this split node. So V is A is the attribute. V are the possible values of that attribute. S of V is a subset that has a particular value V. So that's like all the rainy days or all the sunny days. This is the entropy of the raining subset, right? And this weight tells you what proportion of the items fell into the rainy subset. So it's how many items fell into the rainy subset multiplied by how pure was the rainy subset. So if you get big pure subset, it's good. If you get small impure subsets, or well, it's bad. Or big impure subsets, bad as well. Right. Now, so this is the average purity weighted by the size of the set, the average purity after you have done the split on attribute A. And what is this? This is the entropy before we have done the split, right? So we can compute this number. We can compute the entropy before we do the split. It's because we have some positives and some negatives. That's why we're splitting. So what we're looking at is we're looking at the difference in the entropy before the split and after the split. That's the way to interpret it. Basically, you're trying to say, if I split on this attribute, how much more clear or how much more certain am I going to be after the split compared to before the split about what's going to be yeses and what's going to be no's. So that's the interpretation of that guy. So it's called information gain. Another, if you're coming from a mathematical background, another name for this is mutual information. You're measuring mutual information between an attribute A and a class of labels. Okay, so let's go through an example. We have the wind attribute, so it had 9 positives and 5 negatives. We need these numbers for computing that guy, because that tells us how impure or how uncertain we were before we did the split. So that's the equation, right? It's, so there's 14 total items. So positives, there's 9 out of 14. Negatives, there's 5 out of 14. So that's our entropy, and it's 0.94, right? So you need almost 1 bit, 0.94 of a bit to be certain about yeses and nos before we did the split. Now, after we did the split, we have 2 subsets. This is one subset, and here the entropy is 0.81 in the weak subset, and in the strong subset, the entropy is 1 because we're totally uncertain, right? It's 50-50, 3 positives, 3 negatives. So is it better after the split, or is it worse after the split? Well, that's when we need to take into account the size of these sets. So we're going to take the entropy of the set before, so that's 0.94, and the entropy, and subtract from it the entropy of this subset, and minus the entropy of that subset, but they're not going to be weighted equally, right? This one has 8 elements, so it's going to have a slightly higher weight, 8/14, and this only has 6, so it's going to have a slightly lower weight. Right? So overall, the gain is going to be 0.049 for this particular attribute. So what does it mean? It means that if in the current situation we pick wind as the attribute to split on, we would gain 0.049 bits in certainty. Right? We would become that many bits more certain about the positives and negatives. So now you know how you pick the best attribute. Now you know what the angel does, right? The angel takes each attribute in your data set, computes the information gain, computes how many bits you would gain by doing the split, and then does what? Picks which attribute? With the highest gain, right? Because picking the attribute with the highest gain, that will give you the most clarity that you can get at this point in time.